So today we are going to be doing the final column from 84 to 86. It's going to be 2 questions, the second one with 2 parts, and this will end the review. So let's go ahead and without further ado, let's jump into the first one. So number 85. Okay, so what domain restrictions must be placed on all 6 trigonometric functions so that their inverses can be identified? Okay, so what we remember about inverse functions is that we swap their x and their y. One of the things about all 6 of our trigonometric functions, we know that sine starts here. So let's talk about sine, let's talk about cosine. Cosine starts up top and it does that. And we know tangent does this. If I look at their reciprocal functions, let's talk about cosecant. Let's see, it does this, this, this. Secant starts a little over, so it goes up, but it in essence looks the same. And cotangent, let's see, we know it starts, let's see, it goes through 0, starts at infinity. Awesome. Okay, so now with the inverse, what we want to do is we want to swap the x's and the y's, which presents a problem, because if I swap this function, if I swap the x's and the y's, is no longer a function because it doesn't pass the vertical line test. Neither does this one, neither does this one, neither does this one, or this one. The way that we pass the inverse function test is we do the horizontal line test. Nope, nope, nope. Nope, 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 nope. And so we see the horizontal line test makes all 6 trigonometric functions fail. So let's go ahead and take a peek at what domain restrictions must be placed on all 6 so that we can define their functions. And that comes down to the period. How long does it take this function before it repeats itself? Well, if I limit the domain to only that, I can draw the horizontal line test and it'll be fine. Actually, with this one, I'll have to limit it even further. The horizontal line test is going to break from here to here. I might have a good shot from this point to this point with no repeats. Once I start coming back around that curve, I fail it. So I'm going to place a domain restriction on sine. X must be between these 2 values. So I know that if the period is 2 pi, so if I have a period of 2 pi, that's going to be pi. This is pi over 2, a fourth of the way to 3 pi over 2. That's the domain restriction on sine. From cosine, I kind of move it over. I move it from here to the bottom right here. So for cosine, I go from the top, which is going to be from 0, to the bottom. Okay, and that bottom is going to be pi, because again, I notice that the period is 2 pi. For tangent, I can go all the way up, or I can go all the way up. So I have a domain restriction. I can do this in this full curve, but I know this has a period of pi. So this repeats itself. If this is pi, this is going to be pi over 2, 3 pi over 2. Pi over 2. Oh, pi, and then 3 pi over 2. Oh, this is tangent. So I've got my 3 limitations for my first trig functions. For my next one, I notice that I can't include the full loop. I can include part of the loop and part of the loop, which means in order for this to be a function, I have to only include that part and that part. This, again, has the same period as its counterpart of 2 pi, which means that at this point, I'm at 2 pi. So I'm dealing with pi over 2 to 3 pi over 2. So for sine and cosecant, I have the same limits. For secant, I'm going to have the same limits as cosine. I include the first part in the first part, so from 0 to pi. And likewise, I can do the same thing with cotangent. I can include one full sweep. Now I could include this whole piece, so from 0 to pi, or I could include this one. It doesn't really matter with this one. Just to keep in form with the other two, I'm going to include the same period right here. So from pi over 2 to 3 pi over 2. Boom. And so those are the main restrictions of the 6 trigonometric functions. That way we can have a defined inverse. Okay, so let's take a look at number 86. Okay, we wanted to write the equation of the following graphs. Okay, so this looks like a polar graph. It also looks like a rose petal graph. So with the rose petal graphs, we know that it's going to be R equals A plus or minus either sine or cosine, depending on which area it's going to be centered in. And then we're going to call this B times that. And let's call this N theta. So I need to know a few things. The first thing I need to figure out is how far out do my petals go? How far out they go is going to denotate. With a rose petal graph, we actually don't have this A plus or minus. It's just going to be plus or minus B. So I need to figure out how far out these rose petals go. In this case, I noticed that my rose petals go all the way out to 5, so I know that my B is equal to 5. Second, I need to figure out how many rose petals we have. That's going to denotate my N. So my N, if there's an even number of petals, is going to be half that. This is an odd number of petals, so now my N is exactly that. 3 because it's odd. It's going to be equal. If it was even, it would be half. But it's odd, so we're going to go with equal. The next thing is I need to look at which axis they're centered on. So because it's centered on this axis right here, what I know is it's centered on the cosine. So it's centered toward the cosine portion of the graph. So let's rewrite our equation and say that this is going to be R is equal to the positive cosine. So that means my B is going to be a positive 5 cosine of 3 theta. Boom. So that's 86A. Okay. For 86B, oh, that's an awkward B. Let's take a look. Okay. Okay. So this is one of the limnosones that we have, and so I need to know a few different pieces of information about this. So I'm not going to draw this particular limnosone, but we know that we have either A, the limnosone that has a flat edge. I know that I have the limnosone that has a dimpled edge. So there we go. We have the dimpled limnosone. We know that if that dimple keeps going in, we'll have the cardioid. And then if it goes in even further, I'll have the inner loop. And we know that this comes from the values that if A over B is greater than or equal to 2, I know that if A over B is less than 2 but greater than 1, I know if A over B is equal to 1, and I know if A over B is less than 1 but bigger than 0. So what we've got going on here is I see the fact that I have that inner loop, so I know that my A over my B is going to be less than 1, which means my B is larger. So B is larger than A. Okay. The next thing I need to figure out is how wide does this graph go? Actually, with this, we can go ahead and we can jump into where the equation comes from. So with this, we go into our equation of r equals a plus or minus b, either sine or cosine of n theta. Okay? So let's take a look at the a and the b. So the a is going to be the distance that the graph has spanned to the left and right of this shape. So if we look really, really, really closely, it looks like this graph intercepts at +1 and at -1. So I'm going to say that my a is going to be equal to 1. Okay. So now that we know what a is, we can then further define, I know that this maximum distance all the way out here is going to be a plus b. And if this distance out here is all the way to 3, so if a plus b is equal to 3, and I know a is 1, that means b is 2. Okay, so I figured out a, I figured out b. Now I need to figure out whether it's sine or cosine, which will also tell me the plus or the minus. So if I look at this, I know I have my positive cosine, I have my positive sine, I have my negative cosine, and I have my negative sine. So it looks like this graph is heading out towards my negative sine area. So that tells me that I'm going to be looking at a negative sine equation. And the last thing I know that on these types of limnosomes, the n is always going to be equal to 1. We're not going to see anything just outside of that just yet. So let's rewrite this equation knowing that information. So I take all that and I plug it in. I get r is equal to 1 minus 2 sine of theta. Boom. And there we go.